Hey everybody, today we're going to talk about properties of rational exponents, and I just want to give a heads up that there's going to be lots of examples in this section, so just be prepared to take some good notes, be clear with your examples so that you can go back and refer to them because there's a lot of variation in this section. The first thing I want to start off with is hopefully going to be a quick review of our exponent rules. This whole section is dealing with radicals and fractions, so that's the rational part of our exponents. And so the properties for our exponents that we learned in the previous chapters still apply even if we're dealing with fractions or square roots and so forth. So what I want to do real quick is go through those just as a reminder. So if we have two things that have the same base but different exponents and we multiply, remember that we add the exponents, but we do not change the base. So an example of that might be if I have 5 to the 1/6 times 5 to the 2/6, I'm just making something up, then I would have 5 and I add my exponents. Well, 1/6 plus 2/6 is 3/6, or in other words, 5 to the 1/2. My next property is when I have a power to a power. So if I have something that's got an exponent all to another power, remember we multiply those. So it'd be a to the m times n. So my example for that one might be 8 to the 1/6 all squared. Well, that's going to get me 8 to the 2/6, which is 8 to the 1/3 when I reduce. And you always want to reduce if you can. Next property is if I have two things inside parentheses all to one power, then I can split them up as long as I distribute that exponent. So like this. So ab to the m would just become a to the m times b to the m. So a good example, and this is one that people tend to mess up quite a bit, if I have 4x to the third, then this would be the same as, and maybe I make it to the 1/3, okay? That would be the same as 4 to the 1/3 times x to the 1/3. And then of course you would figure out whatever the 4 to the 1/3 is, and you would go from there. Also, an important one, remember we don't want to leave any negative exponents in our answer, so if we have a negative exponent, we flip it and make the exponent positive. This is the same, this applies as well. If I give you 1 over a to the negative m, then it would become a to the m. It works both ways. So if the denominator, or if your numerator has a negative, it moves to the denominator. If the denominator has a negative, it moves to the numerator, it moves to the top. So my example for this one might be something like 8 to the negative 2/3, and that would become 1 over 8 to the positive 2/3. Then I got one more, or two more, sorry. We've got division, that's always an important one, a to the m, and then a to the n. The key is that the bases are the same. We would subtract our exponents, so that would be like 7 over 7 to the third. Well, the exponent for the 7 at top is a 1, so we're going to take 7 and then to the 1 minus 1/3, which is 7 to the 2/3. So you have to pay attention, but the key is you can't do that if they have a different base. So be very, very careful there that you make sure they have the same bases before you subtract their exponents. And then last but not least, if I have a fraction all to a power, then I can split it so that the top is to the power and the bottom is to the power. So a to the m and b to the m. That has to go to both. So my last example for this one might be that I have 12 to the 1/3 over 4 to the 1/3, and I want to take all of that to the second power. Well, that would become 12 to the 2/3 because we multiply our exponents, okay? And then I would have 4 to the 2/3 because I do the exponent on the bottom as well. So this kind of encompasses more than one property. It takes care of your exponent property here, but it also takes care of a power to a power. Alright, now this is where we get into the brand new stuff. We're going to talk about our properties of radicals. And this is going to be really important that you pay attention to these parts. So the first, there's really two main rules that we're going to focus on. The first one is that if you have an nth root of not two numbers, but two things. It could be two variables, it could be two numbers, anything, or maybe if it's one number, you can split it into the nth root of a times the nth root of b. And that's going to be really helpful if you're needing something to have a like term, where you can, it's almost kind of like factoring something out. You can split it, and then that will usually help you simplify the problem. The same thing works if you have a division, so the nth root of a divided by b. Well, this is all one. It's all underneath the radical. But because we have it to the nth, or it's an nth root of both, we can say the nth root of a on the top, on the numerator, and the nth root of b in the denominator. So we just split it. So let's go through a few examples of these. So let's say example 1, we have the cube root of 4 times the cube root of 16. So this would be more like the rule 1, where we have 2 separated, and this time we're going to reverse the rule, and we want to go so that they're all underneath 1. So we're going to have the cube root of 4 times 16. So we're multiplying them together, and 4 times 16 is going to get us 64. So now what we have left is the cube root of 64. So in this case, the cube root of 64 is 4, because 4 times 4 times 4 is 64. So now let's look at example 2. This would be, let's see, I've got the cube root of 250 divided by the cube root of 2. So these are separated, and there's not much we can do with them as is. We can't take the cube root of 250, we can't take the cube root of 2, so we're going to use the second rule, and we're going to combine them under 1. So 250 divided by 2. Well, 250 divided by 2 gets me 125, so it's the cube root of 125. Well, what to the third power gets me 125? That's 5. And we'd be done. So really, this is the only major thing that you need to know for your properties of radicals. The key is that you can identify whether you need to combine them or separate them, and then being able to simplify. So you might need a calculator handy if you're not very good at cube roots or any fourth roots, anything like that. But hopefully as we practice them more, you guys will become more familiar with them. The next part is if we're going to add or subtract roots and radicals. So the rule for this one basically is that they have to have the same index. So the nth root part has to be the same, and they have to have the same radicand or base. All right. So, and if they do, then we would call those like terms. And you guys know what like terms are, where we can combine them. So, in a polynomial, it's the same concept. It's just going to look a little different than we're used to. So an example for this one might be, maybe I have 7 and then times 6 to the 1, let's see, what do I have? 1/5. And then I have plus 2 times 6 to the 1/5. Well, rather than just typing this in the calculator, I would want to leave it as an answer with a rational exponent. And so what you notice is that we have a 6 to the 1/5 and a 6 to the 1/5. Kind of think of those like x. If I had 7x plus 2x, what would I combine? Well, I'd have the 7 plus the 2, so I'd get 9x. It's the same concept. The 6 to the 1/5 and the 6 to the 1/5 match, so I'm just going to add my 7 and my 2. So I get 7 plus 2 times 6 to the 1/5, which gets me 9 times 6 to the 1/5. And so that would be my answer. So you have to identify your like terms and then add the numbers that are in front of it. Now, it's not always going to be obvious that they're like terms. You might have to do some simplifying before you have like terms, and that's going to be important that you can identify that. So that might look like this example here. So this will be example 4, where we have the cube root of 16 minus the cube root of 2. Well, we can't take the cube root of 16 or the cube root of 2, and we can't subtract them because they don't have the same radicand. Okay, so the radicand is this part underneath here, but they're not the same. So what we need to do is make them the same. So in this case, I could split this. I know I want to have a cube root of 2. Well, what 2 times what gets me 16? In this case, 2 times 8. So I could have the cube root of 8 times the cube root of 2. So all I've done is I've just split it. So now, and I'll bring down my other cube root of 2. What you should notice is that we have a cube root of 2 and a cube root of 2. Well, what's the numbers out in front? What is the cube root of 8? That you can do. Okay, we can simplify the cube root of 2 to just 2. So we're going to have 2 cube root of 2. And if you want to put this in parentheses, that's fine. Minus, and that number out in front is just a 1, and then cube root of 2. And now we can go ahead and combine like terms. Notice that we have the cube root of 2's that match. So what is 2 minus 1? Well, that's 1, and then times the cube root of 2. So there's your answer. All right? So yes, you're going to have to simplify. You have to force it to be like terms so then you can combine them together. You cannot do it as it was in the original because those radicands are not the same. You got to make it into them so that they match. So I want you guys to go ahead and try this on your own. We have the cube root of 5 plus the cube root of 40. So press the pause button, try to split this one up and combine like terms, and then see how you do. Well, what you should see is that you could split 40 into 8 times 5. And notice that when we do that, we get the cube root of 5 and the cube root of 5 to match. Well, so we're going to write that down, cube root of 5, because we know that's not going to change. And then we have a 1 out in front here. Well, what is 1 plus the cube root of 8? Well, you got to know what the cube root of 8 is. The cube root of 8 is 2. So we would take 1 plus 2, which gets us 3. So our answer is 3 times the cube root of 5. And you're done. All right, now we've got 2 more rules to go through and a few more examples, and then I will let you guys on your own. So the first one, this is the same rule, but we've got 2 different cases. And this is if we're dealing with radicals. So if I have the nth root of x to the n, and x is just anything, the rule is that it equals x if n is odd. So what basically happens is that the nth root and the power, the n, they cancel out, and you're just left with what's your base. Okay. If you have that same thing, but your n is even, then it equals the absolute value of x. So it just depends on if the index is even or odd. So let's show some quick examples. So when it's odd, we could have something like the 7th root of 5 to the 7th. Well, the 7 and the 7 match, so that means that we would be left with, and 7 is odd, so we're just left with our base, which is 5, and we're done. So things cancel out. It's really nice. That's why, this is a little side note, that when we take the square root of something like x squared, that we're left with x, because really in a square root the number is 2. So we're canceling out the square and the square root, and we're left with the x. All right? And then for our even, we could have something like the 4th root of negative 3 to the 4th. Well, in this case, the 4's match, so they're going to cancel, but it's an even, so we have to take the absolute value of negative 3. Well, what's the absolute value of negative 3? It's 3. Okay. So there's our 2 different cases. So let's look at a very brief example. And I lost track of what example we're on now. We have the cube root of 64y to the 6th. All right. So right now, they don't match. They don't cancel out exactly. Okay, and sometimes they will, and sometimes they won't. So here's where we're going to branch from this rule. We first want to think about taking the cube root of our number, whatever number we have. Well, what is the cube root of 64? Well, in this case, the cube root of 64 is going to get us, let's see, 4. 4 times 4 times 4. So that's going to get us 4. And then, I guess I'll just write this here. Okay. And then we want the cube root of y to the 6th. Well, 3 and 6 don't match, but here's our little shortcut, okay, and this is going to come in handy. What you want to do is take the power that's underneath the radical, okay, so I'm dealing with my y's right now. I'm going to take the power of the radical divided by my index that's on the outside of my radical, so divided by 3. Okay, and when I do that, what's 6 divided by 3? That's 2. So that tells me how many y's I'm going to have left over. So right here I'd have y squared because the 2 was what I got when I divided. So here's my answer. So 4y squared, and you're done. So let's try another example, just so you can see the pattern. We have the cube root of 27q to the 9th. Okay, so we can start by taking the cube root of 27, and I'm just splitting it. Now you don't have to split it every time, but if it helps you to see it, that's fine. So what's the cube root of 27? Well, that's going to get you 3, because 3 times 3 times 3, that just takes some practice. And if you want to see how to type that in your calculator, just ask and I'll show you. And then we want to take the cube root of q to the 9th. Well, the 3 and the 9 don't match, so we go over here, and we take the exponent of the variable divided by our index. Well, what's 9 divided by 3? That's 3. So that means that we're left with a q to the 3rd. And we're done. Let's try just a few more examples. I want you guys to be comfortable with these because these can be kind of tough. I want you to try, the 4th root of x to the 4th over y to the 8th. So press the pause button and try that out. Alright, what you should have gotten was the 4th root of x to the 4th over the 4th root of y to the 8th. So we could just split it so we can deal with one thing at a time. Well, the top is like our first rule. The index matches, so we're left with x. And then on the bottom, the 4 and the 8 don't match, so we take for the y, 8 divided by 4, which gets us 2. So we're left with y squared on the bottom. So x over y squared. Now the next 2 examples, they're going to be our last examples we go through. These are if it doesn't go in evenly, and this is really important because this is going to be more common. So say I have the 5th root of 5a to the 5th, b to the 9th, and then c to the 13th. So we'll go ahead and start breaking it down piece by piece. Can I take the 5th root of 5? No, I can't. There's no way you can simplify that at all. You can't take something 5 times itself and it's going to get you 5. So we're going to leave that 5th root over here. So the 5th root of 5. Okay. Then, so I've already taken care of that. Then I'm going to move on to my a to the 5th. Well, 5 and 5 match, so I'm left with just an a, and that a goes on the outside. All right. And it's a to the 1st because it cancels out. Then I go on to b, so the 3rd one. Well, 5 and 9 don't match, so we come over to the side. So for my b value, I take 9 divided by 5. Well, how many times does 5 go into 9? Well, we know it goes into it once, and how many are left over? Well, 5 times 1 is 5, and leaves us a remainder of 4. And this is kind of how you used to divide, like when you were little. So what this tells us is that on the outside, we're going to have 1b. So I'm going to stick that here. Let's see. A b that goes there, and then underneath I'm going to have a b with an exponent that's 4. So the rule is the whole number you get tells you how many are on the outside. The remainder tells you how many are underneath. Okay? And then we're going to do the same thing for c. So for c, 5 and 13 don't match, so I have 13 divided by 5. Well, how many times does 5 go into 13? That's twice. And I have a remainder of 3, because 5 times 2 is 10, plus 3 gets us 13. So this tells us on the outside we have 2 c's, so c squared. Okay, and then on the inside I have c to the 3rd. So this right here would be my final answer. ABC squared times the 5th root of 5b to the 4th, c to the 3rd. All right, so it's all about just simplifying. You take one piece at a time, reduce it as much as you can, and then you're done. So let's go through our one last example, and then we'll be good to go. So we have 3 times the cube root of 5x to the 5th minus x times the cube root of 40x squared. So this is combining multiple rules. So the idea here, we're wanting to do some subtraction. So we have to have like terms. And right now we don't. Okay, but we've also got some radicals that we can reduce. So let's look at the first one. Is there anything that we can reduce? Well, we can't take the cube root of 5. Okay, and we've got this 3 out in front. So we know we're going to leave the 3 and we're going to have a cube root of 5 because we can't do anything with that. But 3 and 5 don't match. So we're going to go off to the side where our x's are, and we can take 5 divided by 3. Well, that gets us 1 remainder 2. So on the outside we have an x, and then underneath we have an x squared. So all I did was just simplify this first one. And then I'm going to do the same thing for the second one. So right now I've got a minus x, and I'm going to try to reduce my second part here. Well, you can't take the cube root of 40, but remember we're trying to subtract, so we have to have like terms. Well, so that means we need to break that cube root of 40x squared into something where we can have a cube root of 5. Well, we've got a cube root of 5. 5 times what gets us 40? 8. 5 times 8. Well, in this case, what's the cube root of 8? The cube root of 8 is 2, so we're going to stick a 2 out in front. Okay, and then we've got our cube root of 5. And now we need to see if we can reduce the x squared. Well, they don't match, so we go over to our x value. 2 divided by 3. Does 3 ever go into 2? No, it doesn't. Okay, so that means that we can't do anything with it. We'll have to leave it as it is. So that means there's an x squared underneath. So if you don't get it going into it at all, then you can't reduce it. And now what you should notice is that we have a cube root of 5x squared and a cube root of 5x squared, which is good. So now that means that we can take the 3x minus the 2x, which gets us 1x, and then we keep our cube root of 5x squared. So there's our final answer. Okay, now I know this is a lot of steps and a lot to look at, but you got to look at it piece by piece. Think about trying to get like terms when you're adding or subtracting with radicals. Try to reduce the radicals as much as possible, and then you should be able to combine. All right? If you have any questions, I tried to get as many examples as I could that are going to be similar to your homework. Make sure you're asking for help. If you need more examples, feel free to ask and I will give those to you. Thanks for listening.